Thank you. Thanks very much for the introduction and for inviting me to speak and tell you all a bit about my work. So I'll tell you about quantum theta bases. This is joint work with Ben Davison. So basically about in the early 2000s, Fomin and Zolovinsky defined cluster algebras, and then within a few years, Fock-Goncharov conjectured that cluster algebras should have some canonical bases satisfying some various nice properties, including some nice positivity properties that I'll tell you about. And maybe about around 6 years ago, around the start of 2015 or end of 2014, Gross-Hacking-Keel-Kontsevich, they used ideas from mirror symmetry, particularly from the Gross-Siebert program, to construct canonical bases called theta bases for cluster algebras. And they focused on classical cluster algebras as opposed to quantum cluster algebras. But quantum cluster algebras have been defined by Berenstein and Zolovinsky, and also there's a sort of a dual version defined by Fock-Goncharov. And Fock-Goncharov's conjectures applied for the quantum version, for the quantum cluster algebras as well. Ben Davison and I, we took the ideas from Gross-Hacking-Keel-Kontsevich, kind of used a lot of the main ideas in their arguments and combined them with some ideas from DT theory, particularly DT theory of Quiver representations, in order to construct quantum theta bases and prove that they satisfy these nice positivity properties and basically all the same properties that the classical theta bases satisfy. Yes, this is what I want to tell you about. So first, a bit of background on cluster algebras. So yes, there are certain commutative rings constructed in this very sort of combinatorial way. So I mentioned they were defined in the early 2000s by Fomin and Zolovinsky, and they wanted to create a sort of algebraic and combinatorial framework for understanding this idea from representation theory, this concept of Lustig's dual canonical bases, and this total positivity property that they satisfied. This is a construction from quantum groups, semi-simple quantum groups, and it was this very kind of abstract construction. I think somewhat difficult to understand, but there were parts of these bases that they understood and satisfied some nice properties, and they sort of axiomatized this and used it to build up this definition of cluster algebras. And since then, cluster algebras have shown up in a lot of different places. So I mentioned they came from representation theory and quantum groups. They found a lot more applications there. They're important now in higher technical theory, Poisson geometry, DT theory, and Quiver representations, mirror symmetry, and lots of other areas. The ones listed here are the ones I'll actually mention. And lots of spaces that you might be interested in have cluster algebra structures, semi-simple Lie groups, Grassmannians, other flag varieties and partial flag varieties, Schubert varieties. I mentioned higher technical spaces. Gross-Hacking and Keel observed that all log-Fabio surfaces, for certain definitions of log-Fabio surfaces, satisfy or have cluster algebra structures, and that was sort of they were studying log-Fabio surfaces, and then this observation led them to generalize what they were doing for surfaces to other cluster algebras. So cluster algebras, as I mentioned, they were defined by Fomin and Zolovinsky, and they're constructed. There are these rings constructed in this combinatorial way. Fock-Goncharov took a more geometric approach and defined cluster varieties, and these are constructed by gluing together a bunch of algebraic tori called clusters. And they're glued using certain birational maps called mutations. So here's a little kind of schematic picture that shows kind of how I prefer to think of mutation. This interpretation is really due to Gross-Hacking-Keel. So basically, a mutation is it's some birational map that takes a form something like this. Basically, one of your variables gets multiplied by 1 plus some monomial maybe raised to some power, and then your other variables are unchanged if you choose them in a certain basis. So yeah, so to map something like this, x maps to x, y maps to y times 1 plus x, sort of a prototypical example. So this would be some map from c star squared to c star squared, or a birational map. And what this does is, so on the left we have a copy of c star squared. So think of it as it's a toric variety, and I've these dashed lines are supposed to be some boundary divisors at infinity, so that it actually looks like c star times p1. And on one of these boundary divisors, we blow up a point, the point where this 1 plus x is equal to 0. So we blow up this point, and that gets us this variety up top, where we have this exceptional divisor, this e tilde, and then we contract this like p1 fiber f here. We take the proper transform of that, and then we contract that, and that gives us a new toric variety. So this mutation is this blow up, blow down. So this birational map between these toric varieties, or between their big torus orbits. Think of that as some isomorphism between Zariski open subsets, and we can use that to glue these tori together. And so that's what mutation does. And when you do this gluing, what you end up with is basically the top picture, the thing that you have after the blow up, up to I think only the point where e tilde and f tilde intersect gets missed when you do this gluing. But if you're interested in global regular functions, codimension 2 stuff like that doesn't matter. So Gross-Hacking-Keel basically said you can think of cluster varieties as just blow-ups of toric varieties. You have some toric variety and you blow up a bunch of stuff in the boundary in a certain prescribed way, and you get the cluster variety. And then what's called the upper cluster algebra is the ring of global regular functions on the cluster variety. And the cluster algebra, which is the thing that Fomin and Solvinsky were originally looking at, they did later also define the upper cluster algebra, I think joined with Berenstein. So the cluster algebra is the subring of the upper cluster algebra, which is generated by the cluster monomials. So the cluster monomials are the elements, these global regular functions, which when you restrict them to some cluster, just look like monomials. So remember, each cluster is an algebraic torus, so the functions are generated by monomials on those, and cluster monomials are actually monomials in some cluster. So now the data that you use to construct a cluster variety or a cluster algebra is called a seed. So I'll focus on skew-symmetric seeds because there's issues with proving the quantum positivity results for non-skew-symmetric cases. First, a seed is the following data. So it's the data of a lattice n, which has finite rank. So you're just like integers raised to some power. A set E, which is typically you view as either a basis for n or maybe part of a basis for n, and it's indexed by the set I. And then this skew-symmetric integer-valued form B on the lattice n. So there's different ways this might be presented. Sometimes people will just give the matrix for B, and this essentially captures all of the data that you want here. Yeah, I like to think of it like this, this lattice with part of a basis in a skew-symmetric form. I'll denote the dual lattice by M. I'll use these angled brackets to denote the dual pairing between N and M. And then for each of these basis vectors EI, we get a corresponding vector VI in M by just inserting it into the first entry of B. So B of EI comma blank, we can view as something in the dual lattice, and that's this VI. And there are some mild generalizations that can be done here. You can say that B might only need to be Z valued on the EIs. You can let it be rational elsewhere, but for simplicity, I'll just go with this. So we get these VIs in M, and then the positive span of the VIs I'll denote by this MO plus. So that's some submonoid in this lattice. And in order to quantize, we're going to need an integer. We'll need another skew-symmetric form, an integer-valued skew-symmetric form. I'll call lambda on the lattice M, which is basically like an inverse to B. So B of EI gives you, or B of EI comma blank gives you VI. Lambda of blank comma VI gets you back to EI. So it's at least an inverse on the span of the EIs. So you might notice that a compatible lambda like this doesn't always exist, but there's always some stuff you can do where you basically enlarge your lattice n. You can think of that as adding extra coefficients. And you can do that in a way that makes it so that then you can find a lambda. You can make it quantizable. Also, there's a sort of a dual approach to, or a dual version of cluster varieties that I won't talk about, cluster Poisson varieties or cluster X varieties defined by Fock-Goncharov, and those can always be quantized without needing this form lambda. But aside from mentioning this right now, I won't really focus on those. Just for simplicity, it's easier to pick one side. But basically everything is almost the same with this dual version. So right, so I mentioned cluster varieties are constructed by gluing together these algebraic tori. For quantum cluster algebras, we want to use quantum tori. So let me start by saying what the classical torus algebra is. So by the torus algebra, I just mean the coordinate ring for the algebraic torus n tensor C star. So in other words, it's C adjoined M, C adjoined the dual lattice M, which is this ring. So it's C adjoined Z to the U for each U and M, modulo this relation that Z to the U times Z to the V is Z to the U plus V, where this addition is in the lattice. And for the quantum version, we adjoin this extra coefficient variable t to our ring. So it's C adjoined t to the plus or minus 1, and then joined monomials coming from the lattice. But then this relation up here, we modify Z to the U times Z to the V is Z to the U plus V times this power of t. And the power of t is given by this lambda pairing between U and V. So it's non-commutative because if you multiply in the reverse direction, remember lambda is skew symmetric, so you'll end up with negative the exponent. Right, and now I'm given a seed. So I've mentioned given a cluster, we mutate to another cluster, and so that's another torus, and we'll glue these together to build the cluster variety. And when we mutate, there's also another seed. So I'll explain the seed mutation. So given a seed S, or that's this lattice N and this basis and this form B, if we pick one of the indices, so one of the basis vectors, then we can get a new seed, mu J of S, associated to this choice J, by we just replace each basis vector with each basis vector EI with some EI prime defined by this. So EJ becomes negative EJ, and for all the other EIs, you apply this piecewise linear map, which either takes EI to itself, or if this skew symmetric pairing is positive, then it adds that pairing times EJ. So just this identity on half the plane and this shear map on the other half. And the rest of the data, the lattice, the index set, the skew symmetric pairing, that all stays the same when you mutate. And again, there's different ways that this can be presented. This is kind of my preferred way, my preferred viewpoint. And then, so this is how we mutate a seed. Now, let's go back to how we mutate clusters, how we mutate these tori to glue them together. So we have this seed S. We can mutate that to get another seed mu J of S. We have a algebraic torus associated to each of these. So remember, these are each a copy of C adjoined M. And the mutation should be a birational map between these tori. So it'll take a monomial Z to the M to z to the m times this. So it's times 1 plus z to the vj. Remember, this vj was that b of ej comma blank. So 1 plus z to the vj to the power of the dual pairing between ej and m. And this can be understood as some blow-up, blow-down map, like I talked about before. And then to construct the cluster variety A associated to the seed S, we just basically keep repeating these mutations and gluing the resulting tori as much as we can. So for any sequence of indices in the set I, you get a corresponding sequence of seed mutations, and then also a corresponding sequence of cluster mutations of these birational maps. And you just use these birational maps to glue all these tori together and get some huge collection of tori that you glue together. Turns out normally you can see almost everything with just a few mutations from the initial seed. But yeah, so you do all these gluings via all these different ways you can mutate. You have this infinite tree of possible mutations, and doing all these gluings gets you your cluster variety. And remember, the ring of global regular functions is the upper cluster algebra, and that's what we went to basis for. So I want to explain the quantum version of mutation and quantum cluster algebras. So first, a little notation. So given a non-negative integer, k, we can define an associated quantum number, k brackets of t, or quantum k. So it's given by this, t to the k minus t to the negative k over t minus t inverse, which can be expanded as this Laurent polynomial on t. The sum of powers of t, and there's k terms here. So if you set t equal to 1, this becomes k. So that the classical limit is back to the integer k. Then we can define quantum k factorial as just the usual, like k times k minus 1 and so on down to 1, but use the quantum versions of all these integers. And then the quantum binomial coefficient is it's like this usual binomial coefficient defined in terms of factorials, but we use these quantum versions of the factorials. And some motivation is so the binomial coefficient is equal to the Euler characteristic of a Grassmannian. I think the Grassmannian of I guess k-planes in R space, and then this quantum binomial coefficient would be the Poincare polynomial, or maybe some shift of the Poincare polynomial for that same Grassmannian. So like the power of t remembers which degree cohomology it came from. So now to define quantum cluster mutation. So remember our mutation, the classical mutation was z to the m maps to z to the m times this binomial to this power. And so this binomial to the power, you can apply the binomial theorem to write this as a sum of binomials with binomial coefficients. For quantum mutation, we basically just take the binomial coefficients in the expansion of this and replace them with the quantum binomial coefficients. So it can be written like this: z to the m maps to the sum of z to the m plus kvj. So with these binomial coefficients, but we use these quantum binomial coefficients. So it's just the expansion of this, but using again using quantum binomial coefficients. So this was defined by Bernstein and Zolovinsky. There's this dual notion I've mentioned defined by Fock-Goncharov, which can be expressed in very similar terms. The way it's normally expressed and understood, though, is not actually in terms of quantum binomial coefficients. I kind of like this expression because it's, to me, it's a bit more intuitive when you see it for the first time, or it seems a bit less intimidating at first. Just replace binomial coefficients by quantum binomial coefficients. But the way that's normally understood is in terms of conjugation by a quantum dilogarithm. So we have what's called the quantum dilogarithm. This so this series. So this is like So if the denominator were just k, then this would just be the Taylor series for natural log. With k squared, it's called the dilogarithm. And then we turn one of these powers of k, or one of these k's in the denominator to quantum k, and that's the quantum dilogarithm. And then we can exponentiate this. So we think of this quantum dilogarithm as living in some Lie algebra, and it exponentiates to some Lie group. So yeah, we take exp of this, get, well, you can also call this the quantum dilogarithm or sometimes the quantum exponential. And conjugation by this is the quantum mutation. So so you can show that this conjugation, I should have had z to the m here instead of z to the n. But yeah, you change that to an m, then this conjugation turns out to be the same as this mutation. So yeah, then to construct quantum cluster varieties, similar to the classical setting now, we take all possible sequences of indices and then take the corresponding sequence of seed mutations to get these different seeds. And then we can similarly define these quantum mutations between the corresponding quantum tori, just the corresponding compositions of these quantum mutation maps from the previous slide. And then the quantum upper cluster algebra. So remember that the classical case was supposed to be the global regular functions for the cluster variety. So that just meant that you're looking at the functions which are actually regular functions or Laurent polynomials under every possible sequence of mutations. Right, being a global regular function just means you actually land in these torus algebras under all these compositions of birational maps. And so for the quantum version, we just do the analogous thing. We want the elements of your quantum torus algebra, which continue to land in the quantum torus algebras under every possible sequence of these quantum mutations. So that's what this is saying. So now, so let's look at an element in this quantum upper cluster algebra. Take a non-zero element f, and we say that this element is universally positive if it has positive integer coefficients in every cluster. So you take one of these compositions of quantum mutations, land in some quantum torus algebra. You express this as some quantum Laurent polynomial with the coefficients are Laurent series in T, and if each of these has positive integer coefficients, f is universally positive. And then a universally positive element is atomic if it cannot be written as a sum of two other universally positive elements. So these are sort of like the like some sort of prime elements or like indecomposable elements or extremal elements of the universally positive set. And if we have a basis for this quantum upper cluster algebra, we say that the basis, so like an additive basis, everything is a sum of elements of this. Strong, and then you expand that as a linear combination of basis elements, all those coefficients will be non-negative. It will be not, or will be, I guess there'll be Laurent polynomials in T with non-negative integer coefficients. So now this Fock-Goncharov conjecture states that the atomic elements should be indexed by the lattice M, and they should form a basis for this quantum upper cluster algebra. And furthermore, this basis should include all the quantum cluster binomials. So all the elements which look like binomials in some cluster, some quantum cluster. And so notice being atomic, automatic, or if a basis consists of atomic elements, it's easy to show that automatically they'll be strongly positive. Also, if you're strongly positive and include all the quantum cluster binomials, you can show that implies universal positivity. then by definition, atomic implies universal positivity without going through this. So this conjecture turns out to be flawed as it was originally stated. Levy and Jelevinsky found that the atomic elements, even in the classical setting, they might be linearly dependent. So then they can't be a basis. And Gross-Hacking-Keel, right, so I should say, so Fock-Goncharov's original conjecture, they really conjectured this for the cluster X varieties. So I mentioned there's this dual version, or these cluster Poisson varieties they construct. So just sort of this dual version of cluster algebras and cluster varieties. And they were really focused on that in their conjecture, though the same conjectures kind of make sense and essentially work for the cluster A varieties. So for this dual version, the X varieties, Gross-Hacking-Keel found that the ring of global regular functions is often just often just C. Like, often there are no non-constant global regular functions, or if there are, there aren't nearly enough. So I guess, let's see, I should maybe say this is really a family of varieties, and maybe you might have functions on the family, but not on each fiber. So basically, there aren't enough global regular functions in general, and so they found you can't have a basis indexed by, for this dual notion, it would be by n. And then there's similar issues with the A version. So basically, I don't think I'm saying it clearly. Just Gross-Hacking-Keel found that often there are not enough global regular functions for this lattice to actually index a basis. So it turns out, though, that the Fock-Goncharov conjecture is still, quite close to being true. There's a couple nice modifications you can make that make it true. So, with this, or the issue with the basis being atomic, basically the cause of that issue is that when we defined universally positive, we only looked at having positive coefficients in each cluster. But it turns out you need a lot more charts than just the clusters in general. So I'll tell you about scattering diagrams in a bit. And basically, scattering diagrams have they have this nice part where each chamber corresponds to a cluster, but then they also have a more complicated part where you might have kind of infinitesimal chambers that correspond to some formal like local coordinate charts on your cluster variety. And when you define universal positivity, you want that to include positivity in these extra coordinate charts that come from the bad part of the scattering diagram. And if you include that, then you get this stronger notion of universal positivity. And so a slightly different version of what it means to be atomic. And that fixes the issue with sort of having too many atomic elements, this linear dependence issue. And then this issue that Gross-Hacking-Keel found with not having enough global functions, you can avoid this by working with a formal version of the cluster algebra. So basically, just with each of your clusters, each cluster was like this CT adjoined M. The lambda is to remind us what the skew symmetric form is. And basically, you just you tensor this with this ring of formal power series. So basically, instead of this torus algebra consists of Laurent series, you extend it to include formal Laurent series or quantum Laurent series. And then you can still talk about mutations with these. And with these, you end up getting a basis, and there are sort of enough global functions. One thing to be careful of is in this setting, you don't technically get a basis, you get a topological basis, which basically just means that you might need infinite linear combinations to actually hit every element. Sort of like how binomials don't form a basis for the ring of Taylor series, because you might need infinite sums of binomials to get a Taylor series, but they form a topological basis. So now my theorem with Ben Davison is that subject to these modifications, the quantum Fock-Goncharov conjectures are true. So the classical version of the Fock-Goncharov conjectures with these modifications is what was shown by Gross-Hacking-Keel-Kontsevich, although they actually didn't address the atomic property. So I did that separately in the classical setting, and then with Ben we could extend that to the quantum setting. So in the classical limit, our quantum bases become the Gross-Hacking-Keel-Kontsevich theta bases, and so I mentioned in general these full Fock-Goncharov conjectures don't quite hold because we need these formal we need to use this formal version, but in a number of nice situations, the full Fock-Goncharov conjecture does hold. So basically, whenever it holds in the classical setting, it holds in the quantum setting. The full conjectures where you don't need the formal version. Although the property of being atomic, you kind of need that modification in most cases, where you have to look at the extra charts. But in some nice cases, it turns out the two different notions of atomic agree. So I want to tell you a bit about where this construction of this quantum basis comes from. And first, I want to tell you about where the classical version of the theta basis comes from. And the motivation for this, it's sort of not actually discussed in GHKK at all. You kind of have to look at the Gross-Hacking-Keel paper on log-Fabio surfaces to understand what their motivation was. But it really comes from the SYZ picture of mirror symmetry. So I want to sort of go over this to say kind of why all these constructions are showing up, like where all these ideas come from. So remember, in SYZ mirror symmetry, you have your space X and the mirror space Y, and these are supposed to emit these dual torus vibrations, special Lagrangian torus vibrations, over some base manifold B. And you can get local coordinates on your mirror in a certain way. So say we have X and we have this Lagrangian torus vibration over B. We can get these sort of local coordinates on B. Basically, you start at a point on B, and you can take some circle living on the torus up above, and you can do this for each element of like the fundamental group of this torus. So you take the circle, and then as you move along B, you look at how the circle up above traces out a cylinder, and you can take the symplectic area of the cylinder using the symplectic form that X is equipped with, and these symplectic areas give you some local functions y sub j on B, and this actually gives B what's called an affine structure. So the structure of a manifold whose transition maps are affine linear functions. So it makes it an affine manifold or a tropical manifold. And it turns out exactly how you represent these circles, if you move them around on these tori, that doesn't affect these areas because these tori are supposed to be Lagrangian. So Stokes' theorem implies that these choices don't matter. So yeah, so you get these coordinates on B. You can take the differentials, d of yj, and that gives you some coordinates on the tangent spaces. And it gives you some lattice of integer tangent vectors. You can quotient by that to get some local picture for what the mirror space Y should look like. This tangent bundle mod integer tangent vectors. So these will look like, the fibers will look like tori over B. And you can get some local algebraic coordinates on this mirror like this. So we have this coordinate yj on B, dyj on the tangent, the tangent spaces. So we look at dyj plus square root of -1 times yj times 2 pi I, and then take the exponential of that. And this is supposed to give some local algebraic coordinates on this mirror. So to some extent, this is heuristic, but I think a fair amount has been made precise. There's a nice paper by Denis Arroux on mirror symmetry on the complement of an anti-canonical divisor, I think it's called. where he kind of goes over where this comes from. And there's also, at least in some cases, a way where you can hope to get some global functions, not just local ones on the mirror. Basically, you take a sum over, instead of just these cylinders up above, you take a sum over all holomorphic disks, which go to infinity in some prescribed way, specified by this direction p. Like roughly, it's like going to infinity in this, so like p roughly corresponds to a tangent, one of the integer tangent vectors, and we're going to infinity in that direction, hitting some boundary divisor associated to that direction with some multiplicity. We take the sum over all such holomorphic disks, which hit whatever boundary divisor with whatever multiplicity, and which have boundary on the torus fiber over some point q. And we can do this thing where we take the symplectic area of this to get what we call y gamma, and then do this just like on the previous slide, exp of 2 pi I dy gamma plus iy gamma, just the same thing as before, but with these disks instead of cylinders, and take the sum over all of these. And this, at least heuristically, is supposed to give some global functions on the mirror. Things get complicated when your SYZ fibration has singular fibers. So instead of just a torus fiber, you might have like a pinched torus like this. And basically what happens is that these holomorphic disks coming in from infinity, they can join up with some other holomorphic disk, which maybe like you have a holomorphic cylinder, which normally wouldn't be able to close up to form a disk. But with this pinch torus, it can close up at that pinch point. And so that gives you these more general types of things that can happen, where sort of in this tropical picture in B, this straight line coming in can now bend when it crosses some sort of wall where these disks coming out of the pinch point come out of. And this results in this sort of wall crossing where on one part, where when you go from one part of B to another part, these local coordinates that we had change. We have some transition map or some wall crossing automorphism. So on the left side here, you might have only, so like this dashed line is supposed to be some wall where suddenly you can glue these extra disks and get some more complicated things. On the left side here, we might have only one disk, but then on the right side, after we cross this wall, you can either go in this, like in this straight line, or you can have this bend. So we have these two disks. So on the left side, maybe you have just this binomial x inverse associated to this disk. And on the right side, you still have x inverse associated to this straight line, and then also x inverse times y associated to the one that bends. And I've factored the x inverse out to make this look like a mutation. So it should be suggestive. So this is a sort of a typical thing that happens when you have singular fibers for your SYZ fibration. When you have multiple singular fibers, these sort of initial walls that come out of them can interact to form new walls, well, sort of like this. You have these disks coming out, they intersect, and keep going in some new way. And then the notion of a scattering diagram is sort of a combinatorial way to keep track of all of these wall crossings that can show up. So you have sort of all of these walls that live in this sort of affine manifold B or tropical manifold B, and they have these functions attached to them that tell you basically about your transition maps. So like if you cross from the bottom left quadrant to this chamber, you might get this transition x inverse maps to x inverse times 1 plus y. So this 1 plus y here is labeling that. And that's the transition that we'd seen a couple slides ago. So yeah, so these walls are labeled to keep track of the transition functions. And broken lines, there's this notion of a broken line, which is sort of a combinatorial way to keep track of these holomorphic disks that come in from infinity. And it keeps track of these disks and the functions that they can, and their contributions to the these global functions, these theta function elements that we're constructing. So this blue curve here is supposed to illustrate a broken line. It comes in the local coordinate system for this initial chamber, the contribution of this would look like just x, the monomial x in that coordinate system. And you cross this wall, it bends in some way, give you x times y. Cross another wall, it bends in some different way. In this local coordinate system, it looks like y. So yeah, so again, at this point, this might be a bit strange because I haven't told you the precise definitions. I will soon, but hopefully you can kind of see heuristically how this data, this combinatorial data, is supposed to be capturing some really rich geometric ideas coming from mirror symmetry. And then taking some sum over broken lines will be how we construct the theta functions. So all right, so that's the heuristic picture. So now I'll tell you more precisely what a scattering diagram is and what a broken line is. So basically, a scattering diagram is a collection of these codimension 1 walls in M tensor R. So this M tensor R, this is supposed to be like that affine manifold B that we had the SYZ fibration over. So we have this collection of walls in here with some elements attached to them. Remember, you think of these as giving you the transition functions. But here we're doing a quantum scattering diagram. So these attached functions will actually be in this quantum Laurent series ring. And there's this compatibility condition that the exponents, the lambda pairing of the exponents with the support of the wall should be 0. So the wall supported on the sort of lambda orthogonal to the exponent. And given a path in M tensor R, we can define an associated path-ordered product. So this is some automorphism of this quantum Laurent series ring, or this formal quantum torus algebra thing. Basically, just whenever gamma crosses a wall, you conjugate if you have some element in here, you conjugate it by the function attached to that wall, or possibly by the inverse of that function, depending which way you're crossing the wall. So you think of this as your different chambers of your scattering diagram correspond to different local coordinate systems, and this is saying when you go from one chamber to another, what your transition maps are, or how you transition between these different local coordinate systems, these different charts. And we say the scattering diagram is consistent if these path-ordered products only depend on the endpoints of gamma, on the endpoints of the path that you're taking. So it's this is basically like a co-cycle condition, saying that these transition maps are consistent with each other. And now, all right, so given these walls, we say that a wall is incoming if these exponent vectors that showed up here are actually contained in the wall. Otherwise, we call the wall outgoing. And then there's a theorem, kind of a standard fact about scattering diagrams, is if you have some initial scattering diagram consisting where all of the walls are like full hyperplanes, then that uniquely determines a consistent scattering diagram whose incoming walls are exactly the ones you started with. So in other words, by adding only outgoing walls, there's a unique up to equivalence way that you can make your scattering diagram consistent. So now in the cluster setting, given a seed, the initial scattering diagram we take will look like this. So remember, we have these basis vectors EI living in N. So their orthogonals in M tensor R will be the supports of our initial walls. And the functions attached to them are these quantum exponentials. And remember, I mentioned before, conjugating by one of these quantum exponentials, it can be interpreted as the quantum mutation that we use to glue quantum tori together, quantum clusters together. So crossing these initial walls exactly corresponds to the quantum mutations out of your initial quantum cluster. Right, and then it turns out the rest of the the rest of the clusters also correspond to chambers in your scattering diagram, and all of these mutations between them can be understood as these path-ordered products where you're conjugating by these functions on the walls. So here's on the bottom, I have a few pictures of scattering diagrams showing up for two-dimensional quantum cluster algebras. So this first corresponds to where all of these correspond to where you have a two-dimensional lattice and two basis vectors. The first is corresponds to where the skew symmetric pairing between your two basis elements is equal to 1, and you end up with one new wall. If that skew symmetric pairing is equal to 2, it gets more complicated. You get some infinite collection of walls that bunch up along some limiting ray. And but still, in this case, every chamber corresponds to a cluster. And then in this case, if your skew pairing between your basis vectors is 3 or higher, you end up with infinitely many walls bunching up along these two limiting rays, and then you have this chamber where it turns out every ray of rational slope is actually a part of your scattering diagram. And so you have all these sort of infinitesimal chambers that correspond to sort of extra local coordinate systems on your quantum cluster variety. So things get much more complicated quickly. Now, a broken line with ends p comma q, where p is something in your lattice and q is some point in M tends to R. This is some piecewise straight path in M tends to R, which follows certain rules. It's only allowed to bend at the walls of the scattering diagram. Each straight segment has some binomial attached to it, and the initial binomial should be z to the p, where p was this chosen element of your lattice. So here p was 1, 0. And then when you and the broken line should end at the point q. The direction of the broken line should always be negative of the attached exponent. And finally, the way that you bend when you cross a wall is when you get to the wall, you apply this conjugation, this wall crossing automorphism, to the attached binomial, and that gives you some maybe some formal Laurent series, maybe some complicated thing, but you just pick one binomial from that Laurent polynomial or formal Laurent series, and you take that to be the binomial for the new straight segment of your broken line. So different choices will correspond to different bends because the direction corresponds to the exponent. Or the direction is negative the exponent. Yeah, so these define our broken lines. And then to define the theta functions, we say that theta sub p comma q is the sum over all broken lines with ends p comma q of the binomial attached to the last straight segment of that broken line. And this lemma of Carl Pomperla-Siebert in the classical setting, and then myself in the quantum setting, says that if you take different choices of q, you get different expressions here, but these different expressions are related by the path-ordered products between these different choices of q. So we can interpret this as saying that that these theta pq's patch together to form a single well-defined global function theta p, and these different theta pq's are just the expressions in different local coordinate systems. Okay, and then my theorem with Ben Davison is that up to equivalence, every scattering function of this consistent scattering diagram has this specific form, this bold E called a plathistic exponential of negative p of t z to the v for some Laurent polynomial p of t. And then our theorem is that this p of t has non-negative integer coefficients. So this E is called a plathistic exponential. So there's some representation theory motivation. It's sort of a algebraization of the notion of a graded symmetric product. I think, I don't know that writing down the formula would be too helpful, but a nice case is that this bold E of negative z to the v is the same as this quantum exponential we saw before. And then more generally, if you have some other plathistic exponential of this form, you can always factor this as a product of quantum exponentials, maybe with some extra powers of t here. Yeah, you can factor it like this. So a consequence of that is that so knowing this positivity result for the scattering diagram almost immediately, or well, pretty quickly at least, implies positivity of broken lines, like the coefficients for the binomials attached to broken lines will always be positive because essentially because of this description of your scattering diagram. And so then from this, you get universal positivity of the theta functions and strong positivity and atomicity, all well, in some fairly straightforward ways. We sort of know how to do those. It's not too hard to get from, once you know positivity of broken lines, getting the rest of this is not too hard. So this theorem is really sort of the key step to unlocking everything else. So see, don't have much time, so I'll try to quickly say a bit about how we get this positivity. So suppose we have a quiver Q without oriented 2 cycles. So a quiver Q is equivalent to the data of a seed, well, roughly equivalent to the data of a seed, where the lattice for the seed n is z to the q naught, where q naught is the vertices of the quiver. So we have one dimension for each vertex. The vertices form our index set. Our basis is naturally, we have a natural basis for the seed of the q0, based on corresponding to each vertex. And then the skew symmetric form is just coming from the adjacency matrix for the quiver. Also, the quiver Q determines a category, the category of representations of the quiver Q. So basically an object in this category is just a choice of vector space Vi for each vertex I, and a morphism from Vi to Vj for each arrow from I to j. And now, given a positive linear combination of these basis vectors Ei, let's call these coefficients Ai, we say that some quiver representation V has dimension n if the dimension of Vi is this coefficient Ai for each index, for each vertex. Now the representations of V with a specified dimension vector, they form a nice moduli space or a moduli stack. So that, there's this nice description as this smooth algebraic stack, just sort of the product of all the possible Hom spaces associated to your arrows, modulo the automorphisms of the vector spaces associated to the vertices. Now also at each point in M tensor R can be viewed as a King stability condition, a certain type of stability condition for these representations. Basically, you say that some quiver representation V is zeta semi-stable if the dual pairing of the dimension vector with V with zeta is 0, and then the dual pairing for this dual pairing for any sub-representation is less than or equal to 0. And if these are strict inequalities, then it's zeta stable. So now the zeta semi-stable representations form a moduli stack, or they form this nice moduli stack. So this is just the moduli stack of the zeta semi-stable representations of a given dimension vector n. And Bridgeland showed that that there's a consistent scattering diagram, the stability scattering diagram, whose scattering function at some point zeta in M tensor R is given by this. So he interpreted this in terms of Hall algebras. Basically, so here we have our moduli stack of the zeta semi-stable objects. We take the compactly supported cohomology of it, this ver is just some shift in the cohomological grading. And then we can take this sort of Euler characteristic of this, or for the quantum version, more like a Poincare polynomial. Yes, so more specifically, this chi thing, this chi of this is given by this characteristic polynomial here. So this cohomology is graded by m plus direct sum z. So the m plus that's basically coming from the dimension vectors, or you apply b to the dimension vectors to get things in m plus, and then the z is the cohomological grading, and then given something graded by this, you can take you define chi of it to be this sum of t to the r z to the m times the dimension of the degree mr part of this vector space, where the r is the cohomological grading part. And then this plothistic exponential I mentioned, if you take the graded symmetric product of v, the characteristic function of that is exactly the plothistic exponential of this characteristic function. So that's where those plothistic exponentials come from. And then it turns out that the stability scattering diagram agrees with the scattering diagrams we saw before, if and only if the quiver Q is acyclic, possibly except for vertex loops, so a loop from a vertex to itself. In the cases where you have vertex loops, we didn't really define this dA before, so you have to extend what we did a bit, but you can make sense of it still and then see if this equivalence. In cases where your quiver is not acyclic, then you need some additional data of a potential function, and then things get more complicated. And even with potentials, it's not clear. It's expected that a potential always exists that makes this equality hold, but it's not really known for sure. So then this integrality theorem of Davison and Meinhardt essentially says that these characteristic functions have the desired form, this plothistic x of p of t z to the v. Some interpretation of this theorem can be used to show this statement that these characteristic functions always have this form. So that gives the result we wanted for the acyclic cases, that the scattering functions have the form we wanted, and then for non-acyclic cases, we can use some techniques from Gross-Hacking-Keel-Kontsevich to sort of inductively reduce your scattering diagram to a scattering diagram with only two initial walls. In the classical setting, you can even reduce that two-wall case to the case of the A2 quiver, just two vertices and one arrow between them. But in the quantum setting, you can't do that last reduction. It doesn't work. But you can reduce to the case where you have two vertices, some number of arrows between them, it could be any number, and then possibly a loop, a vertex loop at one or both vertices. And then we reduce to those cases, and there, we now know that the stability in cluster scattering diagrams agree, and this Davison-Meinhardt theorem applies and shows that those cases have the desired form. And so then by this inductive procedure from GHKK, we show that the scattering diagram in general that we want has the desired form. And so then we get this, this positivity of the scattering diagram and then positivity of everything else, and you can prove these all these properties you wanted about the quantum theta functions. So just to end, I want to talk about one application. It's some work in progress joint with Fan Chin. If you have a surface with boundary and some mark points on the boundary, you can define what's called the quantum skein algebra for this marked surface. And so basically it's you have a bunch of strands that connect mark points to other mark points and also maybe loops on your surface. They satisfy certain relations, like strands crossing like this can be rewritten as using this Kaufman-Skene relation like this. And then some other relations, other quantum skein relations. And Greg Muller showed that these quantum skein algebras have a quantum cluster algebra structure. You can also extend to surfaces with punctures, just then you don't really have the quantum structure. But yeah, there's a generalization to surfaces with punctures. And in these quantum cases, so in general cases, there are certain bases called the bracelet bases. And in these quantum cases, Zoe and Thurston defined the quantum bracelet bases and constructed that these should be strongly positive, meaning you have positive structure constants. And then what Fan Chin and I are showing is that these quantum bracelet bases agree with the quantum theta bases. And then in the classical setting, possibly with punctures, the bracelet bases, the classical bracelet bases will agree with the classical theta bases. And then also on the dual, there's the cluster X varieties that Fock-Goncharov defined, and they have some dual version of the skein algebras there. We also show that the Fock-Goncharov basis elements and their quantizations agree with the theta bases and quantum theta bases there as well. So then automatically we get this, by the properties of quantum theta bases, we get this strong positivity, and then also also show that they're atomic. And actually, for these cases from surfaces, the different notions of atomic with respect to the clusters or with respect to your extra coordinate charts, it turns out these notions almost always agree for these surface cases. So it's even sort of the original notion of atomic that Fock-Goncharov considered actually holds here as well. Okay, so that's I guess that's it for what I wanted to talk about. Thank you.